Hey guys, in this video I would be revisiting the formulas of Fourier transform and inverse Fourier transform, and we would try to decipher what these formulas are trying to tell and what are its physical significance. Then we would be moving to two-dimensional Fourier transform and again try to understand what those formula are trying to tell us. Then at the end we'll take some examples. So in the last video, we derived these Fourier transform and inverse Fourier transform formula. So this is your inverse Fourier transform, and this is your Fourier transform. So we derived it from the basics of Fourier series, which Fourier himself had proposed to solve those heat equations. So you can observe that fx here, this in IFT, fx is basically proportional to proportional to f of k into e to the power minus I kx dk over k varying from minus infinite to plus infinite. So let us assume a value of k. Since k is varying from minus infinite to plus infinite, let me assume a value of k, let it be k1. Fine. So if I assume this to be k1, then my this function will be f of k1 e to the power I k1 x. Fine. So we know that the real part of e to the power minus I kx tells me the physical signal. Actually, this is basically in the phasor form. So from phasor form, if you want to derive what is the physical signal, you need to take the real part of that signal. If that signal is f of x, then you have to take it the real part of f of x. For more details, you can read section 9.7 from the book Principle of Electromagnetics by Sadiku. So in this section, they have described what is a phasor form and how to retrieve the physical signal, and if you have a physical signal, how to go to phasor form. Actually, doing mathematics in phasor form is very easy. That's why we always take the phasor form, and later we just take the real part of that phasor form to get the exact signal. So this, what is this e to the power I kx then? So if you take any, let's say, signal which is let us suppose in time domain, if I take a signal e to the power I omega 1t, basically this is a wave. It's a wave with angular frequency omega 1, and the signal correspond to this would be, the physical signal correspond to this would be real part of e to the power minus I omega 1t, which is basically cos omega 1t. So we know that this signal would look like something like so this would be time, this would be amplitude, so this is cos, so this will go like this, this is, let's say, t, so t1, let it be t1, then basically omega 1 is 2 pi by t1. Fine. So this particular signal, it corresponds to a spatial wave with spatial free angular spatial angular frequency k1. Fine. So for this is basically, this is x, then again the real part would be the signal would be cos of k1x. So in x it would be like this, from here to here it would be, let's say, lambda 1, the wavelength of the signal be lambda 1, then k1 will be equal to 2 pi by lambda 1. So you know that if you change k, you're basically changing the lambda, the value of lambda. Fine. So what if, okay, so this particular signal, from here you can see it is getting multiplied by f of k1. Okay, so this will give me basically the product of fk e to the power minus ikx for a neighborhood around k1. So what if I change the value of, if I take another value of k, let's say for k equals to k2. So you know from here that k1 and lambda 1 are directly not inversely proportional, but if you change the k, basically you are changing the lambda. So when you are changing k, you will have some lambda 2. So this would be, the lambdas would be different, and this time it would be multiplied by f of k2. So if I take all the values of k in this interval, what I can write is basically f of x is some constant into let's say this is k1, this is lambda 1, so this would be k1 into f of k1 plus this is lambda 2, so this would be k2 into f of k2 plus I am deliberately trying to make these lambdas different so that you can visualize it, into f of k3. Similarly goes on. So f of x is basically, you have all these angular spatial waves corresponding to the angular spatial frequencies, and they are multiplied by a envelope of fk. So basically this will help you to visualize what is f of x. So again, it's just the summation of different values, different spatial angular frequencies multiplied with their particular coefficients. So this is how you can visualize any f of x in inverse Fourier transform. So now we will try to extend the one-dimensional Fourier transform and inverse Fourier transform to two-dimensional Fourier transform. So these were the formulas corresponding to one-dimensional Fourier transform, and these are the formulas corresponding to two-dimensional Fourier transform. So as you can see, in basically two-dimensional, we have introduced another variable along with x, that is y, and in the frequency domain now, instead of having k, we have kx and ky. So coming to the formula, uh, this f of k is now f of kx and ky. This e to the power I kx is split into e to the power minus I kxx plus kyy. uh, because of introduction of a new independent variable, now this single integral becomes double integral, so it goes from minus infinite to plus infinite. And similarly for the Fourier transform formula. So uh, this is the formula for two-dimensional Fourier transform and inverse Fourier transform. Now let us try to see what these formulas are basically trying to tell us. Fine. So again, coming to the point where we would like to see what these formulas are trying to tell us. So in case of 1D, what we did is basically we took the function, we took a value of k, and then saw what really happens if I change the value of k on the physical signal. Similar thing we would be doing here. So let me assume the value of kx as kx1 and ky as ky1. Fine. So these kx and ky are basically from minus infinite to plus infinite. I am taking them from their respective ranges. So what really happens? Now this particular function becomes f of kx1 ky1 e to the power I kx1 into x plus ky1 into y. So let's put some special attention towards this term. So we know that this term would be equal to some constant. So this kx1 plus ky1 into y is basically some constant a1. The value of constant might change. Fine. So it's kind of constant which is a variable. So what does this shows? So recalling from the concepts of geometry, basically this is a straight line. So let me put this term in more familiar way. So this kx goes there, so y would be basically minus kx1 by ky1 into x plus a1 by ky1. So now you can more appreciate that it's a straight line with a slope. This is a slope, this is the y intercept. So when you will draw this thing in the Cartesian coordinate x and y, so basically this is a assuming a means assuming a is let's say for this line it's 0, then assuming then we know that this particular line will pass through origin. So you can change the value of a1. There is no constraint on the value of a1. So even though if you change the value of a1, the slope won't change, only the intercept will change. So it might happen that for some value a2 might have a line like this. So this is for a1, this is for a2, maybe for some a3 you'll get a line like this. Slope won't change. Slope won't change. Once you have fixed the value of kx1 and ky1, this slope is not going to change. Only changing this a basically changes the y-intercept. Fine. So you can see, okay, so there is one more thing, that e to the power I of a would also be equal to e to the power of I a plus 2 pi. So not all a1 would give you a different value for this particular function. Basically, it would be repeating itself. So from this and from this, we can conclude that basically e to the power of this is a plane wave. It's a plane wave in some direction, let's say alpha. So I assume that this is alpha. So what would be the value of alpha? So you know that this alpha is basically perpendicular to the slope of the line. So from this geometrical mathematics, we know that for a perpendicular line, the slope m1, if the slope of one of the line is m1 and another line is m2, then this has to be -1. So putting this thing here, you can get the slope of this line would be this. So if this is the slope, then what would be the angle? We know that this is basically tan of alpha. So I would easily calculate from here, alpha equals to tan inverse ky1 by kx1. So we also have some concepts like k alpha. So basically k alpha is under root of k alpha 1, or let's say k alpha 1 would be here. So kx1 plus ky1 ka whole square. Fine. This you can write in terms of lambda as well. So this is, you know that this is basically 2 pi by lambda. So this will go to lambda x, lambda y. So you can feel now that this particular function is basically a plane wave in alpha direction. Fine, which is multiplied by this f of kx1 comma ky1. So now what if I change the value of these values which I'm taking? Now I would be taking kx2 and ky2. What would happen? So you'll see that basically these the value of changing, by changing the value of kx and ky, you will be changing the value of alpha, the direction in which it is moving. So you will again get, from this particular function, you will again get a plane wave, but maybe in some other direction. Let's say now in this direction. So this wave is moving in this direction. For some other wave, let's say kx3, ky3, you might get a wave in some, let's say, this direction. So what does this formula is telling me? This formula is basically telling me that you vary your value of kx and ky, and we know that when I vary the value of kx and ky, basically I'm changing the direction in which the wave is propagating. So, and then you multiply it with the envelope function of f, kx and ky, which basically gives the frequency content of that particular kx and ky. So again, like in one dimension we did, what I can do is I can now say that f of xy is basically some constant, which is basically 1 by 2 pi. This is xy, so let's say this into f of kx1 ky1 plus into f of kx2 ky2 plus, let's say there would be one wave like this also, assuming kx3 ky3 plus some wave, let's say in this direction, into f of kx4 ky4 and so on. So now you can feel basically that this f of fxy is some constant multiplied by the wave which is going in every direction into their particular frequency component. So this is how you can visualize a two-dimensional Fourier transform, in fact the inverse Fourier transform. So till now we have learned how we can visualize the IFT, and basically we have learned that it's the superposition of different spatial frequencies multiplied by their respective uh, coefficients. Now let's tinker with the signal and see what effect these tinkering have on the frequency spectrum of that particular signal, or if I tinker with the frequency spectrum of the signal, what effect will it have on the spatial signal. So what are the basic things which we can do with a signal? So before starting, let us assume that f of x and f of k are the Fourier transform pair. So what are the basic things which we can do with this signal fx? So one thing which we can do is basically we can shift this signal. So if this is x and this is your amplitude, what I can do is basically I can shift this signal to some other place, let's say by x naught. So if it is f of x, then if I'm moving it towards right hand, then it would be f of x minus x naught. So what will this x naught cause in the frequency spectrum? What is the effect of this x naught? So what is the formula of Fourier transform? So the formula of Fourier transform is basically f of k is minus infinite to plus infinite f of x e to the power I k x dx. So what effect does this f of x minus x naught, let's say this x naught, will have on the fx? So for finding that, what we can do is basically plug in this formula here. We'll see that this is f of x minus x naught e to the power I k x dx. I can replace this x minus x naught with mu, and then this x will be mu plus x naught, and then dx would be equal to d mu. Replacing these stuff here, what I'll get is basically minus infinite to plus infinite f of x, f of mu e to the power I k mu plus x naught dx d mu, sorry. So what I can do is basically I can remove this factor from the integral. So this would be what? E to the power I k x naught f of mu e to the power I k mu d mu. So you can see that this is basically the Fourier transform of f mu. Mu is basically a dummy variable here, so I can replace it with x, and I know that this is the Fourier transform. So I know that for the Fourier transform of f of x is basically f of k. So this would be f of k. So as you can see, that new f of k, so this would be, let us assume this is f dash k, which corresponds to this frequency transform of this signal. So you can see that basically when I shift this signal, it does nothing in the frequency spectrum. It just adds a phase term. So a phase term is multiplied to all the frequency component. No new frequency is basically generated. It's just that the phase of that spectrum changes, and we know that by how much it changes. So what if I have, let's say, shift the signal in frequency domain. So if I have a signal in frequency domain, this is k, this is amplitude, and now I shift it to, let's say, k naught. So if it was f of k, this would be f of k minus k naught. So what you can do is basically you can apply the same formulas, and what you can see is this time you can do the all mathematics, but this time you have to use the inverse Fourier transform formula. What you will get is basically f of for this particular signal, you will get Fourier transform pair of e to the power I k naught x f of x. So again you can see basically that it is adding a phase term to the existing signal. So moving the signal either in frequency domain or in the spatial domain basically induces the phase term in the other domain. So this is very clear from this example. What are the other things which we can do? Yeah, so we can flip the signal. So what I can do is this is called space reversal. What I can do basically is if I have the x, I can replace it to minus x, which is equivalent to saying that I have this I will be taking images when I put a mirror at x equals to 0. So this is basically would be flipping the signal. So what really happens when you flip the signal? So again you will go through this process, that what will happen, and what really comes out is that your okay, let's do it. So that's very easy. So f of k, we know that this is d of x. So nu f dash of x k is basically e to the power, now I'll replacing with minus x to the power I k x dx. So what are the things which I can do is that I can have this minus x equals to y. So if I have this, then I'll have minus of dx equals to dy. Fine. So now I'm replacing this with this will go to minus I k y, and this would be minus of dy. So when you will put this minus sign in front, what you can do basically is you can represent this thing as this. So this is again a Fourier transform, but then the point is that this is not same. So this corresponds to f of minus k. So it's very easy to play around with the signal and see what effects it is causing to the frequency spectrum. Okay, so what next? We can also, what we can do is basically we can scale up the axis or shrink down the axis. So for that, let us see. By saying scale up or scale up, what I really mean is basically a thing which you will encounter again and again in this series of video. So we know that a lens can basically it provides a magnification. So what really happens is that if this is a signal, then this signal will be magnified. So I can say that the x-axis is basically stretched. So if I have f of x, then I can say what will happen if I do f of ax. A can be any value from 0 to it can also have a negative value, that's not an issue. Fine. So what will happen? So again we'll push this thing into the formula. So this time the formula would be f of ax to the power plus jkx dx. Now we will replace ax equals to let's say what, mu. Then I'll have d of x equals to d mu by a. So replacing this, what you will get is basically this would be mu, then x would be replaced by mu by a, and this would be d mu by a. You will pull this 1 by a factor out, and then you can see that f of mu to the power plus, I can put this in one bracket, and this would be d mu. So this is basically same as f of k by a. So it's very easy to see what really happens with when you play around with the signal. You can do a lot of other things. I've done some basic stuff here. You can do a lot of other things like doing conjugate. So again, by doing conjugate, what you get is if you have a signal f of x and you do the conjugate, I'm not doing it here, so it will basically the frequency spectrum would be minus f star minus k. You can derive it. It's It's really very easy. Then I like to move towards a very important theorem, which is a duality theorem. Duality theorem. So, what really happens in duality is they talk about what if you take the of Fourier transform of, let's say, f of x. They basically talk about the Fourier transform of the Fourier transform of signal. So they try to establish dual pairs, which can be which is easy to basically solve. Means this particular property helps us to solve a lot of complicated signal very easily. So what we are basically looking forward is Fourier transform of the Fourier transform of fx. So this is what this we know, this is basically f of k, right? So okay, I'll do this. Since this is the symbol of Fourier transform, this is an operator, bold it. So this is basically f of k. So you are taking the Fourier transform of f of k. So what you can do is you can push this in the formula f of k e to the power plus I k x and dk. Please remember this is dk because whatever be the variable of this, it has to be same here if you are doing the Fourier transform. Now what you can do is you can replace k with x and x with, let's say, k, and let's see what happens. Then what happened is this is f of x e to the power. What I'll be doing is like I'll creating one minus sign. I can certainly write this in this form, and this would be x. Can you recall this, what really it is? If you can recall this, this is basically, if you can recall it from the inverse Fourier IFT formula, which is f of x is basically 1 by, so this is small f, 1 by 2 pi under root this f of k e to the power minus I k x dk. So isn't it giving you a same form, except there is 1 by 2 pi term missing, and this x is minus x. So comparing this to this, can I write this as 2 pi f of minus x? So that's why we say that this, from this dual property we can find a lot of things. Like if you know the Fourier transform of let's say f of x, you can find the Fourier transform of f of k or the inverse. So basically they form a dual pair, and people have tabled down a lot of dual functions, and knowing them really helps in calculation. So this particular property really eases out a lot of calculations and help us to directly derive results from some other results which we know many of the times. So before starting the example, I would like to discuss a very famous function So that function was given by, as most of you know him, PAM Dirac. So probably you guys know that which function I'm talking about. So I'm basically talking about Dirac delta function. So according to this function, if you have a x-axis and this is amplitude, so this function, Dirac delta function, which is denoted by this del, basically says if it is x equals to 0, that the value of this function remains 0 throughout this x-axis except at x equals to 0, where it shoots up, and then it suddenly comes down to 0 again, and then it remains 0 till positive infinity. So the function is basically delta of x is 0 if x is not equal to 0, and it goes to infinite if it is 0. But there is also one more condition, that integration from minus infinite to plus infinite del of x d of x is 1. So basically, even though this particular value is going till infinite, the integral, the area under this particular peak is only 1. So the definition of Dirac delta function not only includes this one but also include this one. So this one plus this one defines what is delta function. So there are again a lot of variation. So if you have this del of x minus x naught, so then you have functions here, then there would be sudden increase here, and then again 0 here at x equals to x naught. Fine. So there is one more very famous property associated with Dirac delta function, that is related to integral of the integral when you multiply a del function with another function. So let us assume that I have another function f of x. Fine. And what I'm doing is basically multiplying del of x with f of x. So what will happen? What do you think? So what if you can see graphically, if this function f of x is like this is f of x, and we know that del of x is basically, I'll use another pen. So del of x is it will go till infinity, and then it will come back to 0. So basically there is only one place where these two functions are meeting. This is this place. So only here I will have non-zero value of this multiplication. So you can feel that this is basically, if you go through this is del x dx equals to 1. So this is kind of, you are doing the sampling. So when you are multiplying this particular signal with this, everything is 0. This whole area is 0 because del x is 0. This whole area goes to 0 because again their del is 0, but only here at x equals to 0 you have a value. So whatever value this function will have at 0 will be basically this del of x fx. So integral going from minus infinite to plus infinite del of x f of x is basically, d of x is basically f of 0. Another variation of this particular formula is if you have, let's say, del of x minus x naught f of x d of x, then you know that there would be a peak at x equals to x naught. Then this function will take this particular integral will take the value of this fx at x equals to x naught. So this is f of x naught. Fine. So these concepts will help us to uh, uh, to uh, to be used later. So what is this? What is the Fourier transform of del of this? So you can see what is the I am talking about Fourier transform of del of x. So you can put this thing in the formula del of x e to the power I k x dx. So from this particular formula we can say that this is e to the power I k 0. Just in place of x, this particular thing you can treat it as f of x, and when you so the value of this integral is f of 0. So this f of 0 is basically e to the power I k 0, which is 1. So you can feel that if this is your x-axis and this is your amplitude and this is your amplitude and this is your k-axis, then here you can feel that this is defined by this particular function. So this is like this goes till infinity here at x equals to 0, and then it comes back. So this is x equals to 0, and what is the Fourier transform of this is basically 1. So for every value of k, what you are getting, if this is 1, then for every value you are getting 1, regardless of whatever angular spatial frequency I am talking about. So this del function has got all the angular frequency components. Each of the component is contributing equally to this particular thing. So this is spatial domain, this is a spatial frequency domain. So just keep this in mind that the frequency spectrum of a delta function is basically 1, and you can use the duality theorem to get the frequency spectrum the Fourier transform of this particular function, which is basically 1. So that will be, if you can recall, that would be basically 2 pi times del of minus x. So del of minus x is basically del x here, because there is only one component at the center. Fine. So let us discuss a few more examples. Nothing better than to start with sine k naught x. So it's a spatial function which varies in x. This is k naught, so you can get the lambda naught from 2 pi by k naught. So this is lambda naught. This is 1, this is minus 1. So this is basically sine k naught x. So what I'm trying to do is basically trying to find the Fourier transform of sine k naught x. Fine. So we can directly apply a formula here. So we can directly apply this here. K naught x e to the power I k x d of x. We can directly use this formula to get the Fourier transform of this particular signal. But let's try to think that what can be its Fourier transform without going into the formula. So we know that Fourier transform basically tells the frequency component of spatial signal. So basically when you do Fourier transform, what you get is what are the frequencies from which this particular signal is made from. Fine. So what is the frequency? You can see what is the spatial frequency, spatial angular frequency from which this particular sine k naught x is made from. You can clearly see that this is a single frequency function. So the sine of k naught x has only one frequency, angular frequency, which is k naught. Right? There is only one angular frequency, angular spatial frequency to be precise. So what do you think would be its Fourier transform? So going by the definition of Fourier transform, which says that it tells me the frequency component or angular frequency component of the spatial signal, I only have one particular angular frequency in this signal, right? So the frequency spectrum should also have one particular frequency and rest of them should be zero. So from this definition, what I get is basically this particular thing should have one delta function. We know that delta function basically symbolizes only one value where it will go to infinite and then it will come back, as we have already discussed. So the Fourier transform of sine k naught x should be a delta function at k naught, because this particular function contains only one angular frequency component. For example, if I had, let's say, sine of k1x plus sine of k2x, then in this signal I know that there are two frequency component, k1 and k2. So in the frequency spectrum you should get one at k1 and one at k2. So this is how you can visualize the Fourier transform of any spatial signal. So this sine or cos, they are very easy to visualize because they most of the time contain only one frequency component. So it's easy to visualize now. So we were trying to find the Fourier transform of sine k naught x from the formula. So let's try to use some property to solve this. So this f of this can be written as e to the power I k x minus e to the power minus I k x by 2i. Fine. So basically since f is linear in nature, you can remove this, and you basically need to find, sorry, this is k naught, this is also k naught, so I k naught x and minus f of I k naught minus of I k naught x. So now recall that property that if this f if fk and f of x was Fourier transform pair and I displaced it by some value k naught, then it just had a minus I k naught x f of k. So this was the effect on the f of x, sorry, f of x. So you can see that in the time domain I already have this e to the power I k naught x, right? So I can write it as e to the power I k naught x into 1 minus f of e to the power I k naught x into 1. We have just now seen that del of x is del of x and 1 are Fourier transform pair. Fine. So if I have 1 in time domain, then from duality what will I get? 2 pi del of minus x, which is basically 2 pi del of x. Fine. So I know that this would be, sorry, 2 pi del of this would be k minus k, and this would be also k. Fine. So applying this here, what will I get? So I have this thing here, so from here I can see that this is this, so this would be here and there would be a minus k naught sign if there is minus here. So if it is plus here, this particular function collapses to 2 pi del of k plus k naught minus 2 pi del of k minus k naught. Fine. And there is one 2 pi I here. So you can see that there are two components, del of k plus k naught and del of k minus k naught. So when you will draw the magnitude spectrum of this particular function, what you'll get is one signal at k naught and one signal at minus k naught. Since these functions are symmetric, that's why I'm getting the same, that's why I'm getting the mirror images at minus k naught. So this is what we got when we were doing the mathematics also. So this was what we were getting when we were trying to use the definition of Fourier transform to get, only that we were not able to get this component. So physically there is no negative spatial frequency, but in case if you can somehow make sure that this particular frequency shifts in this direction, then you can see the effect of this particular frequency component.